Welcome back. This is going to be my final vignette on probability theory and puzzles in biological problems. And what I have in mind this time is going to culminate in what's known as the Poisson distribution. But the puzzle that I want to pose for us is related to one of actually many examples where the same sort of question will come up, and it has to do with counting. So what I show you here is a microscopy image in the center of some yeast cells, and labeled in red you see a probe, which is shown on the upper left. The probe is used to actually hybridize with an mRNA of interest, and what we're trying to find out is how many mRNAs are there per cell. And what you see in the lower left is a distribution. So the way I want you to imagine this experiment is rather simple, at least in conception, if not in practice. So the conception is that we have a bunch of cells. Each one of them is expressing some levels of mRNA for our mRNA of interest, and we put in these fluorescent dyes attached to probes that hybridize with our mRNA. And so the essence is we go through and count, and then we make a histogram. And so what you see on the lower left is this histogram, and there's a curve that goes that's associated with that, and that curve is the outcome of the analysis that I'm going to give now. So that's basically the result of a fit to the so-called Poisson distribution. Now, in order to think about the production of mRNA, I'm going to have this sort of null model in mind, which is that I have some promoter of interest. This is RNA polymerase. And this thing basically spins off RNA at a rate r. So I want you to think of this basically as a little factory, and the little factory produces mRNAs, and those mRNAs are then degraded at rate gamma. So that's the entirety of our model for what I'm going to refer to as a constitutive promoter. And what we're interested in doing is we're interested in trying to explain, if you like, the histogram that tells us the counts. So I'm going to call this P of n, and this is the probability of finding n mRNA molecules in a given cell. And then the x-axis is n, the number of mRNAs, and this bin is 0, 1, 2, 3, 4, and so on. And so each bin has some height, and so I'm gonna draw my distribution as such. Although, as you saw already at the top here, this distribution looks a little different from what I'm drawing, and it doesn't matter. The essence of what I want to say is unchanged regardless of what picture I draw. So this guy is P0, the height of that skyscraper. The height of this skyscraper is P1. This is P2, etc. So Pn is the probability of finding n mRNA molecules in a given cell. And what I want to do now is I want to see if I can develop a strategy for computing this distribution. And so my logic for achieving that is that I'm going to assume that the system is in steady state. And what that is going to mean is that the flux across each one of these interfaces has to be balanced. What do I mean by that? So what does the green arrow mean here? Well, how do I go from being a 0, being in the column 0, to being in the column 1? The way I do that is by the synthesis of an mRNA molecule in the time step delta t. And the way I go from being in column 1 to column 0 is that in time step delta t, an mRNA molecule is degraded. So to think that through, what we're going to do is we're going to basically write a balance between adjacent skyscrapers. So balance across the 0, 1 boundary. How does that go? Well, what I'm going to say is that R delta t times P0 has got to be equal to gamma delta t times P1. So this is the probability of transcription. And so, and this one is the probability of a decay event. And basically this assertion is what I'm going to be calling throughout the course detailed balance. And basically it's a statement of equality of fluxes, and so I can solve this thing, and what I find is that P1 is equal to R over gamma times P0. So that's our first result. Okay, now let's try a balance across the 1, 2 boundary. This one's a little bit more tricky, relatively the same. So I have R delta t times P1, this is the transcription, has got to be equal to 2 times gamma delta t times P2. The tricky part, or the part that might actually puzzle you, is why do I have a 2 here? What's this 2 for? The reason is that I have 2 RNA molecules in my cell of interest, and either of them in the time step delta t could decay. And so I have to account for the fact that there are 2 candidates for the decay event. Okay, so I can solve this recursively again, and what I find is that P2 is equal to R over 2 gamma times P1. But using what we learned in the previous balance, I see that as 1 over 2, and then R over gamma squared P0. To do that, I used this result up here, this one. Okay, I took this result for P1, and I plugged it in right here, and that leads me to this new result. And so I now can say that P2 is 1/2 R over gamma, that's squared times P0. So that's our second relationship between the probabilities. Okay, we're going to do only one more, and this one's going to be the balance across the n-1 and the n interface. So here I have that R delta t times P n-1 is going to be equal to n times gamma delta t times Pn. And thus Pn is 1 over n and then R over gamma P n-1. Now we can see from our previous work that we can just keep on repeatedly plugging in, and I'm not going to do it. I leave it as an exercise for you, but what we get out is 1 over n factorial R over gamma to the n power times P0. So the general term is Pn is equal to 1 over n factorial R over gamma to the n power P0. So this tells us the coefficients, how all the coefficients are related to P0, and P0 is the only magnitude that we have not determined. So if you go back to this histogram, what we've done is we've figured out an expression for each and every one of these other guys in terms of P0, and now we're going to establish P0 itself by insisting on normalization. What do I mean by normalization? Well, the probability of of having 0, 1, 2, whatever, the sum of all these probabilities, n equals 0 to infinity of Pn, has got to be equal to 1. In other words, this is a probability distribution. It tells me the relative probabilities of all the different possible ways of looking at a cell and finding mRNAs. And we know that when we sum over all those suite of possibilities, we have to get 1. So now I'm gonna plug in the result from the previous recursive solution, and what I have is 1 over n factorial r over gamma to the n power p0. And just to be clear about this, I could write this out as p0 plus r over gamma p1 happened. Let's see if I can recover. Okay, sorry for that brief delay. I'm probably not going to edit it out. So r over gamma p1 plus 1/2. Oh, sorry, that's p0 there. Plus 1/2 r over gamma squared, and p0 again. I just keep on going. 1 over n factorial r over gamma to the n power p0, and then just keep on going. And so this is the same as p0 times n equals 0 to infinity of 1 over n factorial r over gamma to the n power. And this whole thing has got to be equal to 1. Now, I'm gonna give a little vignette on Taylor series, so you'll need to go look at that, but I'm just going to make the assertion right now that this is the same as e to the r over gamma. This is the Taylor series. This series is the Taylor series for the exponential. And so this tells me that p0 is equal to e to the minus r over gamma, because p0 e to the r gamma equals 1, and so I basically divide through. And so now I've got my full distribution. P of n is 1 over n factorial r over gamma to the n power e to the minus r over gamma. And I remind you, by the way, that m star, the average number of mRNAs, is r over gamma. So I could also call this lambda, just for the purposes of connecting with the language of Poisson distribution. So P of n is equal to 1 over n factorial, and then m star to the n power e to the minus m star. And this is called the Poisson distribution. And I'm going to give the students in the course an opportunity to play around with this. But the Poisson distribution is a probability distribution. It's a discrete probability distribution that runs from 0 to infinity, and it tells me the probability of finding n as our outcome. I guess I had a few asides here. One of them is just to comment on what does this distribution look like. And so here I plot for you several different values of the average quantity. Note something very strong and interesting about this distribution is that it's a one parameter family. What do I mean by that? It means that if I want to find out if something fits the Poisson distribution, I simply have one parameter, which is m star or lambda, whatever language you want to use, r over gamma. One parameter determines the entirety of the distribution. So if I'm confronted with data such as this, and I want to actually ask, is this Poisson or not, the procedure is very simple. I find the average of that distribution. It determines m star, and then I plot the distribution. There's no other freedoms that I'm allowed. So that's one point that I want to make. So this set of curves just shows you a bunch of different versions of the Poisson distribution for different choices of the average. And note that if lambda was less than 1, this thing would actually not have a peak. It would just be monotonically decreasing, which is kind of interesting to see. Um, the next thing I guess I wanted to say is I wanted to give you a little bit of a sense, and we'll work out some of these in the homework. The the Poisson distribution has been used in all sorts of really interesting and different ways, and the flying bombs per square mile in London during World War II is really interesting because the thinking there was some neighborhoods in London were hit quite a few more times than others. Some were hit as many as 5 times, and some were hit 0 times. And this led to speculation about whether or not there was targeting going on within the city limits. And there's a similar thing happened in the context of death by horse kicks in the Prussian army, because certain units had multiple people killed by a horse kick and others had no people killed, and they wondered whether this was due to some faiblesse of the commanding officers. And in fact, in both of these cases, you can show that they're consistent. What the observed numbers are consistent, in fact, with random processes where somebody's got to be the loser, and rather than bad commanders or targeting of bombs over London during World War II. And so with that, I think I've said the main substance of what I want to say. A lot of this will actually be absorbed in homework, and I'll probably, as I said, I'll give a little vignette about Taylor series, and also I will give probably another little vignette about the Poisson distribution by the numbers. In other words, how it applies to specific case studies.